Hey there, folks. Here's a problem that involves a square wooden board with a target on it. We're provided the mass of this board and its side length, which I'll refer to as lowercase l. To make things easier to see, let's shift our perspective so that we're viewing this target from the side, like this. The plan here is to shoot right at the bullseye using a bullet that has the mass and velocity given above. The bullet will impact the target and get lodged inside. This causes the board and the bullet to rotate backwards as a single object. The first thing we need to do is figure out the angular speed of the board right after the impact. Following that, we have to figure out the maximum height achieved by the center of the board during that rotation. Then finally, we need the minimum bullet speed that would make this board do a complete rotation about the bar that it's connected to. To solve part A, we're going to need the vector equation for angular momentum. Since we were given the velocity of the bullet, it would be a good idea to replace the momentum vector with mv. Let's take another look at our picture and see how this all ties together. The first vector in the cross product is our position vector, which is directed from the point of rotation to the line of action of the force from the bullet that will act on the board. There's only one force that can do that in the x direction, and that's the contact force of the bullet on the board once it reaches the target. We don't have to worry about calculating its value or anything like that. All we need to do is just identify it and draw its line of action, which is represented by that dotted line. With that done, we can now draw our position vector. Next up in the cross product is lowercase m, which refers to the mass of the bullet. And finally, our velocity vector will point in the same direction that the bullet travels. Now, since the position vector and the velocity vector are not perpendicular to one another, we can't use the same approach as we've done before. Instead, let's take a moment to review a helpful reminder. This says that the cross product of any two vectors can be found by multiplying the magnitudes of the two vectors and the sine of the angle between them. The n hat at the end represents a generic unit vector. Its purpose is to point the magnitude of the cross product in some direction. And that direction is always perpendicular to a plane, which contains the vectors a and b. If we apply this to the angular momentum equation, we get the following. And here I've left off the unit vector at the end because we need to figure out which direction the angular momentum vector points in. The axis of that direction is what we'll substitute into the unit vector. The easiest way to get that direction is to use the right-hand rule. If you're not familiar with what that is, it goes like this. You take your right hand and you point it along the path of the first vector in the cross product, like this. Then curl your fingers through the smallest angle towards the direction of the other vector. Notice that it's a smaller angle going counterclockwise in this position towards V. So your hand should look like this. Here you can see that our thumb will be pointing towards us, out of the screen, which is what we typically define as the positive z-axis. So this means our generic n hat unit vector will be a z hat vector for this particular cross product. So now we know the magnitude and the direction of the angular momentum vector. Let's say that r is the magnitude of the position vector and v is the magnitude of the velocity vector. Then we can rewrite our equation like this. There's a bit of a problem here, though. We don't know the value of r or theta. So we need to find a way to relate those to something else that we do know. notice that there's a length of r sine theta over here. And that length extends from the bullseye all the way up to the top of the board. That's the same thing as L divided by 2. So let's make that replacement in our equation. The next thing we'll do is take advantage of this relationship between angular momentum and angular velocity, which we should substitute in as well over on the left-hand side. Since we're dealing with multiple objects here, let's add a subscript on I, indicating that we're using the moment of inertia sum of the board and the bullet. And here's what that moment of inertia sum looks like. The first piece in the parentheses is for the board, and the second is for the bullet, which we're approximating as a particle. Before we do anything else, let's square that inner L divided by 2 piece to get the following. And with that done, our next step is to divide both sides by this sum on the left. I'll distribute the 2 inside the parentheses, and since we have a single L upstairs and L squared downstairs, we can cancel out a single factor of it, which will leave us with this. At this point, we can plug in our numbers and see what we get. No matter how you've set up your picture or defined your system, you should arrive at the same angular velocity magnitude of approximately 5.46 radians per second. And that's our answer to part A. For part B, let's go back to our picture. We want to solve for the maximum height of the board's center during the rotation. The easiest way to do that is to set the center of the board at y is equal to 0 when it's in the equilibrium position. Then once the board and the bullet reach the farthest point in the swing, the center will be at some maximum y position above 0. And this is where the conservation of energy equation comes in. Over on the left, the center of the board starts the rotation at y is equal to 0. So it has no initial potential energy. And there's no frictional effects happening either. So we can get rid of those two terms over on that side. Then on the right, at the farthest point in the swing, all of the kinetic energy will have been converted to potential. This leaves just a single term on both sides. And we can be a little more specific with what we mean by initial kinetic energy by introducing translational and rotational kinetic energy terms. Now, since the center of the board wasn't moving when we shot it, the translational kinetic energy term is just 0. Let's clean this up and plug in the definitions for what remains. And here I'm using subscripts as a reminder that we need to account for both objects. We want the maximum y value here. So let's divide both sides by the mass of both objects, mg. We can use the same expression that we had for the moment of inertia sum back from part A. And for the sake of consistency, let's square that inner L divided by 2 term in the numerator. There's nothing left here to cancel or simplify further, so we're free to start plugging in our numbers. You should end up with a maximum height of approximately 0.0317 meters. And that's the answer to part B. In part C, we want a bullet velocity that's large enough to make this board do a complete rotation. And for that to happen, the center of the board needs to reach this upward position. The question is, what's the new y value of the center of the board up there? Thankfully, it's really easy to find. Since it's half the length of the board from the center to the rotation point in the lower position, and again, it's half the length of the board from the rotation point to the new center position, then The y value of that new upper position is just the sum of those two half lengths, which gives us L. So our bullet speed needs to be large enough to adjust the y value of the center of the board from 0 to L. We can figure out that bullet speed by using the conservation of energy again. And since the approach is largely the same, we can fast forward through a couple of the steps. Everything that's canceled out here is everything that we canceled out earlier in part B. So nothing changes there. And like before, it reduces to a single term on both sides, and we get the same result that we had previously. But this is where we take things in a different direction. Instead of solving for the maximum y value, which we know already, we want to isolate omega on the left-hand side. Let's start that process by dividing both sides by the moment of inertia sum, and multiply both sides by 2. If we take the square root, we get omega, just like we wanted. We're going to use this with something we figured out back in part A, which said that the magnitude of the bullet's angular momentum is equal to I omega. Since we're trying to figure out a new velocity in this part, we will divide both sides by ml and multiply both sides by 2, which isolates v over on the left-hand side. Next, we can plug in our square root expression for omega and then simplify it. In the numerator, we're multiplying a moment of inertia sum by the square root of 1 over the same thing. So essentially, we're taking I to the first power and subtracting a power of 1/2. And the leftover 1/2 power of I is equivalent to the square root of I. That means we can take that variable and stick it under the square root with everything else, like this. Next up is to replace I with the sum we've used a couple times now, and I'll square that inner L divided by 2 piece once more. One other thing I'll do is distribute the 2 that's under the square root sign into the parentheses. This shortens our result a tiny bit, and once we plug in the numbers, you can see why that might be helpful. It's a very long equation. When I enter all of that into the calculator, I get the following bullet velocity, which I've rounded to the nearest whole number. However, our values in the problem description all had 3 significant figures. Therefore, we should report the velocity result to 3 as well. So once we do that, this will be our official answer to part C. All the parts are now done and our problem is finished. As a helpful reminder, here's a recap of all of the answers that we've collected along the way. And that's it for now. Thanks for watching, everyone. Have a great day.